Hi everyone, and welcome to our video on a vector application involving forces. So if we are having a problem that involves forces, what we would use is Newton's third law, which is telling you you'd want to look at all of your forces in the x component or horizontal components, and they should add up to make zero. And all of our forces in the y component should also all add up to be zero. So Newton's third law is just saying that if we have a force, there should be an equal but opposite force to hold this thing into space. Okay, so here we've got two ropes holding onto a weight. So what we'll do, and it says find the tension or force in each rope. What we will do is redraw it where we make the weight the center. And let's put our axes down. So we'll put it an XY axis. And what the weight is doing, so I will put that in red so we can see it. So the weight is trying to go straight down because of gravity. So those ropes are holding on to it, but if the ropes are weak, it'd break and it goes straight down. Okay, so the gravity is trying to make it go that way. Okay, so that's, I'm going to mark that in red too. That's that same vector being shown. Okay, so that's the weight. I'm going to do W for weight. So there's my marked vector. And then these two would be holding up the weight. So it's pulling a vector this way to keep it in the suspended. And let's go ahead and do purple. This one is going that way to hold it up too. Okay, so all of these, there's three vectors in motion here. The two that are holding it up and the one that's pulling it down. So those we can also get sketched. Okay, so this is, I'm not really drawing them to scale. So the red one would probably be a lot longer compared to these two, but that's okay. And then our purple one is something like that. All right, I'm going to call this purple one T1 because it's on the left, and this blue one T2. All right, and when it says find the tension, they are, so now that I've got things labeled, they are wanting us to find the magnitude of these. So that's the tension that they're talking about, but we really want it in component form first. All right, so using this picture, I want to get those angles in standard position. So T2, I want to figure out what that angle is. Same with T1. I want to figure out what that angle is. Let's keep it in purple. So I want that angle also. The weight angle we know. So that goes to 270. Okay, so we know the magnitude of the weight. So let's mark that kind of, I'm just going to put it right next to it into the picture. We know the magnitude's 120. That is the actual weight. And then it has an angle of 270 degrees. So that's our key information for the weight. And then we want to do it for our two T's, our T1s and T2s. All right, so let's figure out where to get those angles. Well, back to my original picture. So it gave us a 60 and a 30. We have, let me mark it in black ink. If I were to make a perpendicular right there, well, that means I have a right triangle. I have 60 and 90, which means this is 30. All right, and so if I make another dash line, so I'm just kind of making the connection between my two pictures. If that's 30 right there in the dash line to the purple, that means I would know 90 plus 30 would be 120. That would be the angle in standard position. Okay, so we do know that. So I know the angle. I'm just going to keep it in colors and just have them next to each other. Oops, and I did write one notation poorly. That is the magnitude, the weight. I should have put the absolute values on it. So the absolute value of the W, or the magnitude of W, is 120. Now, what we want to do is find our magnitude of the tensions. We don't know that. So I'm just going to leave it blank. So that means we'll use it as a variable as the magnitude of T1. And then in the blue, still I can use my right triangle here to kind of help me. If that's 30, that means this is 60. and then I have another right angle. That means that is 30. Okay, so in my picture, my other picture, there it is in standard form, 30. So I know that angle is 30 degrees, but I don't know its tension, the magnitude. That's what I'm trying to find anyway, so we'll leave it as such. Okay, so I'm just putting equals. We don't know. All right, however, I can still write all of these in component form. Okay, so now we're going to put them all in component form. So I've got the weights in component form. Would be the magnitude of the weight, 120, cosine of the angle, 270 degrees, comma, magnitude 120, sine of 270 degrees. And then we can evaluate this. Okay, so this becomes 120. Cosine of 270 is 0. And then 120. Sine of 270 is -1. So our weights in component form, I'm going to put it to the side here, is 0, comma, -120. Okay, and we might have been able to know that without drawing the full picture, because still this is showing the weight should go straight down. There is no horizontal component if something's going straight down. That's why that's 0. And then something that's going down is negative in our usual notations for directions of math. Okay, so that is our W. And then now let's set up our T1s. Our T1s and T2s. So still keeping it in purple. So our T1, we don't know the actual magnitude. That's okay. We could just write the magnitude notation and put in our cosine of the 120, and still the magnitude notation, sine of 120. And then we'll simplify what we can. So we've got our magnitude, we don't know, we'll just leave it alone. But cosine of 120 we could write as -1/2, comma, magnitude still of T1, we don't know. Sine of 120 is positive radical 3/2. And so I'm just going to kind of rearrange some things here and say our tension number 1 as a vector is -1/2 of the magnitude T1, comma, radical 3/2 magnitude T1. All right, so there's our T1 written the best we could. Then we've got our second one. Let's keep it in blue. So our T2 is still, we don't know the actual magnitude, so we'll use the variable, the magnitude of T2, but we can fit in cosine of 30, comma, magnitude of T2, sine of 30. And to save some space, cosine of 30 is radical 3/2. So I'm just going to go ahead and do this right away. I'm just rearranging. So cosine of 30 is radical 3/2. And then the magnitude of T2, comma, sine of 30 is 1/2. And then the magnitude of T2. There we are. Okay, so those are our 3 vectors in component form. All right, so now we're going to use the Newton's law portion, Newton's third law, where we know the horizontal components, so this one, and this one, should all add up to be 0. Okay, so we know the sum of the horizontal components let me fix my spelling. Horizontal components sum needs to be 0. Okay, so that means we've got, for our problem here, we have 0, just to write it in, plus the -1/2 T1. So I'm just showing in parentheses, so each one, let me even put the 0. So the 0, then plus the -1/2 T1, plus the radical 3/2 T2 should equal 0. And then I'm going to clean this one up one more time to the side. So I put the parentheses to show the substitution, but we could just write it as -1/2 magnitude of T1 plus radical 3/2 magnitude of T2 equals 0. And then we'll do it with our vertical components. So I'm going to do that in this dark blue. So the horizontal component sum should be 0. So should the vertical components. Vertical components sum also should equal 0 according to Newton's law here. So that means that's the negative 120. So that's this part, the negative 120 plus this radical 3/2 magnitude of T1 plus this 1/2 magnitude of T2. All should add up to be 0. And then, well, let's rearrange some things. So the negative 120, I'm going to just add to the other side. So I'm going to write this as radical 3/2 magnitude of T1 plus 1/2 magnitude of T2 should equal 120. Okay, so I just rearranged some things. Okay, and so what we've got now in this problem is a system of equations. So in the black ink and the blue ink, we've got a system of equations here. So we're going to solve this by any method that we really want to use to solve it. What I'm going to do, so we're running low on room, I think we can fit it. What I'm going to do to solve it is I'm going to, so I have the term with the magnitude of T1 are opposite signs already. So I'm going to multiply my top equation, all terms, by square root of 3. So if I do that, what we would have, let's put it right below. I think we can fit this in here. We would have negative radical 3/2 magnitude of T1 plus radical 3 times radical 3. So this is distributing to all of them. Okay, so radical 3 and radical 3 would be 3 over 2. And then the magnitude of T2. And then 0 times radical 3 is still 0. And then I still have the blue equation that I'm just going to rewrite right underneath it. So radical 3/2 magnitude of T1 plus 1/2 magnitude of T2 equals 120. And so there they are next to each other. And the reason that I multiplied by the radical 3 is because now I can add the two equations together. And when we add them together, notice the first terms are opposite but equals. So that means they would zero out. Then I do have 3/2 plus 1/2. That would be 4/2 or 2. So this is 2. And then the magnitude of T2. So 2 times the magnitude of T2 equals 120. So looks like we can solve it now. If we just divide by 2, we've got it. So divide both sides by 2. We do now have, okay, so let's highlight it. So this is our equation that we're solving. And I want to write it to the side since it's tough to see. I'm going to put my T2, well, it's over here. Let's write it there, 60. Okay, so there was our magnitude so far. Okay, so the tension in T2 is 60. Let's figure out the tension in T1. All right, so T1, that means we can go back to one of our equations. So we have two equations there that we can use. I'm gonna mark it in green. All right, so I have my T2 answered as 60. I'm gonna plug it into this one. Okay, so it's up to us which one we want to use. I don't know if either of them are easier or harder. This one is what I think I want to try anyway. So I'm going to put my star here and say I've got radical 3/2 magnitude of T1 plus 1/2. We're saying that the magnitude of T2 is 60, so I'm just subbing that in, equals 120. Okay, so I subbed in 60 for that T2, and I just needed to rewrite it over here because it's a long problem. And then now we can start to solve it. Okay, so 1/2 times 60 is 30. So we've got radical 3/2 magnitude of T1. That is 30. To save space, I think we need to subtract it over right now. That would be 90. And then to get t1 completely by itself, we would need to multiply by the reciprocal here. So times 2 over radical 3. And then that would give us our magnitude of t1, which is 180 over radical 3. Now that we can do some simplifying. Multiply the top and bottom by radical 3. And we will get 180 radical 3 over 3, which finally simplifies to be 60 radical 3. Okay, so that is an exact value answer. Let's highlight it in a different color. Let's do pink. Okay, so we use that equation to get our T1. So 60 radical 3. And I just kind of put it back in the table. I guess officially we should probably put the units on it. So these would be in pounds since the weight was in pounds. So we've got the tension, magnitude of tension 1 is 60 radical 3 pounds. The magnitude of tension 2 is 60 pounds. There we go. So we found it. We found what they wanted. Okay, and so with the physics problems, we can still kind of see if it sort of makes sense for us here. Notice in our picture, T1, the one that was in purple, is mostly going upward. It's doing the majority of the lifting for this problem. So it should be the bigger number. Yeah, 60 radical 3. Whereas this horizontal one, that one's not doing as much. Okay, so it's not helping as much. Okay, so it's like if these were movers, the purple's like the big brother, the blue's like the little brother. It's not helping as much as we would want it to. Okay, so the red is going straight down. The vector that's up here that's going more upward is the purple. Okay, so that's why these numbers should hopefully kind of make sense. And if we need to change them to decimals, that's fine. If we did change them to decimals, one last thing about this. Okay, so I'm just going to type in 60 square root 3 to the side. So over there, I'm just going to say 104. I'm going to round it. Okay, so that one is 104 pounds. Notice that these two numbers, the 104 and the 60, do not add up to 120. Okay, so that the weight was 120. That's fine. It shouldn't. Okay, so most likely it would not. Okay, so that's fine because what the Newton's law is saying is the components individually should add up to make things become 0. Okay, so it's not like this 120 and these just cancel out. Magnitudes alone isn't determining it. It's the component form that's doing stuff. Okay, so anyway, that's it. Okay, so long problem. Draw your picture. Get your component forms going. That's how this one was also. Draw pictures. Get your components. Okay, so, and often again, it's just adding some things together. This one required a little bit more. Okay, but that's it. There's our vector stuff. Okay, so if you have any questions, please let me know. Otherwise, thanks for watching, and I'll see you again soon.